Hello everyone, welcome to the first lecture session of Unit 5. Unit 5 is all about static timing analysis. In this session we will look at the concept and the flow. Some of the concepts are, since the constraints part is very similar to design compiler, there will be some repetition of the concepts of the constraints, but now we will go much more deeper into, so in synthesis we are much more focused about the performance, but STA we are focused upon the fact that the chip should work in all possible components. So we will look at the STA as a concept in the sense that what are the principles behind the flow. We will look at some mathematical equations related to the constraints. So it is better if you have your pen and paper ready before continuing forward. So the agenda is we will look at the part where STA fits in the ASIC design flow. We look at the importance of STA. We learn. We'll look into the operating conditions in some detail. Then we'll go on to the timing paths and constraints. We'll have a relook at the different sort of constraints that STA checks. We'll look take a look at the clocks. However, there will be a separate session in which I'll discuss the clocks in much more detail, being the clocks being the most important part of the constraint. We look at something called timing acceptance, and then we look at the flow part. Is that what all steps does STA contain? So this session will give you a nice overview of STA, and the following sessions we will look at each of the part in more detail. Like in one of the sessions we look at clocks in more detail, we look at exceptions, we look at the interconnects and so on. So this is the ASIC design flow. So what we are focusing on in this course is on the synthesis part, and plus we are focusing on also we've all seen that the job of a synthesis tool like design compiler is to convert RTL into gates given a proper set of constraints, right? So I'm assuming that constraints. So yellow is the output or the input. The blue part represents the flow part or the tool part. So RTL is input to synthesis. The output is gates. Netlist plus constraints. So constraints are again input. They are input also, and when we synthesize, we write out the constraints from design compiler in one of the formats. One of the formats is called LTC, which is understood by most of the place and route tools. And these constraints plus the gate level netlist goes as input to the backend tools for flow planning, place and route. And the output of place and route is a post layout netlist and a parasitics. So the difference between so now you have a post layout netlist and a so now the process of formal verification can be used to verify that the netlist after synthesis is functionally equivalent to RTL. Please note that formal verification is not vector based. It's it is again a static method. So the coverage is very good here. So it can be used to check that. In fact, it can be used to verify that any two designs, whether they be in netlist form or RTL form, are equivalent, are functionally equivalent. So RTL versus the typical flow is RTL versus pre-layout netlist. So this netlist after synthesis we'll call it the pre-layout netlist. So RTL versus pre-layout netlist. Second step is pre-layout netlist versus post-layout netlist. Now this is the functionality part. Now we come to the timing part. STA is used to make sure that the netlist is good from timing point of view, and this STA is called post layout STA, which takes into account the constraints. So it takes into account three things: the constraints, the post layout netlist, and the parasitics. These three are the inputs that go into an STA tool like prime time, and using the process of STA we make sure that the design is good for manufacturing, good for fabrication. This whole process of making sure that design is good for manufacturing is called sign off, and the output of this process is the GBS. So the place and route, there are a lot of backend verification checks that run on place and route netlist. Most of the popular ones are LVS and DRC, and once we have done sign off using prime time, LVS and DRC using the backend tools, we can be sure that the design is good for fabrication. The output is GDS. It is a graphic data stream file that we send it to the fabrication lab like TSMC, and they use it to manufacture the chip. So STA is done at two levels. The post layout STA I was talking about. There's one more STA done at pre-layout level. What we were doing in design compiler. So we were reporting timing in design compiler. We were checking the constraints in design compiler. All this is part of the pre-layout STA. Now the pre-layout STA only helps us in finalizing the constraints and nothing more. Otherwise, any timing result at pre-layout level is not valuable and good enough for sign-off. Sign-off has to be done with complete parasitic data. So the idea of layout netlist is to clean up the constraints, make sure you have all the exceptions in place, make sure the clock frequencies are correct, make sure that your design does not have big violations, or in fact if it has zero violations of synthesis. So this will, the pre-layout STA will make sure that the synthesis netlist is of good quality. But the real violations, the real timing problems will only come after the layout has been done. Hopefully we'll see some examples in the lab. Then we'll do one session about with the post layout STA, that is with the parasitic. So what STA checks? STA checks all possible paths. It's not vector driven. The simulation on the other hand is vector driven, in the sense that you give some values at inputs and you expect some values at the outputs, right? And you have to make sure that you cover all possible combinations. It is not the same with STA. STA is not vector driven. It checks all the possible timing paths in the design. Checking is quite fast compared to dynamic timing simulation, compared to the verification that you do with providing the stimulus. It does not replace simulation. The important fact is it only checks timing. It is not a functionality check. How do you check functionality? By doing verification plus formal verification. So STA does not replace functional verification. STA is comprised of majorly two parts. First part is delay calculation, second part is timing. That means first delays are calculated, then they are checked against the constraints. What are the types of checks that are performed? Setup, hold, recovery, removal, etc. You can also have some sophisticated user-defined data-to-data timing constraints for few of the interfaces. There are some interfaces which you need to check that one data line arrives no later or no faster than some timing constraints with respect to some other data signal. You could have these kind of checks. Then clock gating, we saw clock gating in design compiler. There are clock gating setup and hold checks which we can do with SPA. Minimum period and pulse width checks can be done. All design rules can be done. Minimum maximum transition time, capacitance, fan out, all these. Again, important point, all these checks that comprise sign off will be done at the post layout level. Now when we talk about STA, we have to talk about operating conditions. Since STA is done at multiple operating conditions, just try and compare this with synthesis. Synthesis is always done at the worst operating condition. Why? Because we are only concerned about the performance of the design. But here we are concerned that the chip should work at all possible operating corners. These corners are called operating conditions. P, V and T. T is for process, V is for voltage, T is for temperature. Now what does process mean? Now on a particular wafer and on a die, let's talk about wafer. A wafer has multiple chips. Now all the chips are not going to have same performance. The chips on the corner of the chips which are on the periphery will have different performance when compared to chips that are placed in the middle of the wafer. Now let's talk about the die. That is one chip. Now on one die, not all NMOS and PMOS will behave in a similar fashion. Some of them will be faster, some of them will be slow. Right? This is called process variation. STA, in fact, the whole purpose of STA is to make sure that your chip works in spite of these process variations. There are two types of variations. I'll try and fit in a lecture which talks about variations, because STA is very tightly tied with how the variations take take place in the chip. So some of the variations come under the category of systematic variation. That means these variations affect either all the wafers in a similar fashion or all the dies on the same wafer in a similar fashion. So for example, let's say you are targeting a 65 nanometer process. Now let's say the process, the whole fabrication process by a particular fabrication lab is not optimized, and there is some error in their formula or some error in the manufacturing process, which will result into all devices that have fabrication value greater than 65 nanometers. This is called a systematic variation. It can be used. Systematic variation can be corrected by making some corrections in the fabrication flow. So if the fabrication guy finds out that all the devices on a 65 nanometer technology node are not actually 65 nanometers, they are, let's say, 67 or 68, then the fabrication guys need to make a correction to make sure that systematic variations are minimal. Second is called random variation. On such a small scale of manufacturing, let's say again we talk about 69 nanometers, not all PMOS and NMOS devices will have the same channel length. They will most probably follow a Gaussian curve. We'll see an example of that. And the average of that, most of the devices will have channel lengths that are very close to 65 nanometers. Some of them will be beyond 65 nanometers. Some of them will have channel lengths that are less than 65 nanometers. So this type of variation is called random variation. It is modeled by Gaussian distribution. Let's talk about voltage. All the cells, all the instances don't get same voltage. There is IA drop in the power rails. Even the power supply does not provide. Let's say you are targeting a 1.0 volt power supply. Even the power supply is going to have some variation, maybe 1% or 2% in the power supply. So all the cells don't get the same voltage. Let's talk about temperature. Chip will heat up during operation. Not all parts or all cells on the chip will heat up at the same degree. So there will be. So one part of the chip will be different than the other part of the chip, whether it be in terms of process or voltage or temperature. STA should guarantee that chip works across different corners, right? This is called corner-based STA. In today's world, we do corner-based STA, but there is also something called statistical STA, which is gaining importance. Just because of the fact that all such defect parameters, all such variations can be captured in a statistical way, and it will. So now, as technology shrinks, the number of corners are increasing. So we'll not talk in detail about this in this lecture. I'll probably present one more session on variation. There we will see how and in what manner the variation is affecting the STA form. So all the discussions we have in Unit 5 will be focused on corner-based STA. That means we'll have well-defined corners, and on each of these corners we have to make sure that our chip meets timing constraints. So this is what I'm talking about. So now the delay of a cell at a library, at a standard cell library level, depends on the input transition and output load. We have seen that. So delay is a function of input slew, the load, and now every technology that you have on every corner you have one technology. You have each cell. The delay will be characterized for each corner that we have chosen. So for each PVT. So ultimately delay depends on PVT. For one PVT there is one library. In each of those libraries you have a cell, and characterization is based on the input slew and output load. So there are 5 parameters there: PVT, slewing, and load. Now let's look at one particular parameter. Now there are hundreds of parameters: channel length, thickness of the oxide, and so on. There are so many dielectric of the oxide, and so on. So there are so many parameters that are affected by the variation, by process variation. Let's look at one: channel length. Now if you look at the channel length on, let's say we choose 65 nanometer technology node, and we measure the channel length of each and every transistor on chip, we will see that a graph of something of this kind will emerge, right? Graph like this is called a Gaussian curve. The Gaussian curve is centered around a typical value. In this case it will be 65 nanometer, and there will be some devices which show channel length which is less than 65. There will be devices which show channel length greater than 65. So the distribution looks like this. So this is x-axis is channel length, y-axis is number of samples. Now let's plot two such parameters. One is channel length. Now we on x-axis there is channel length. Now okay, let's first clarify some doubts about the Gaussian curve on the left. Now this Gaussian curve has two parameters. One is called the mean or the average, which is a typical value. Other is called the standard deviation. Standard deviation tells us what is the width of this curve. Now how wide is this curve? Now typically up to 3 sigma. Sigma is nothing but the standard deviation. Typically more than 99% of this area comes under plus minus 3 sigma. That means 65 nanometer, let's say the channel length is the average, and let's say the sigma value is 1 nanometer, for example. So 3 sigma means 3 nanometers. So this more than 99% of this area will come under the values of 65 plus 3 and 65 minus 3. That is from 62 to 68. It will if you take the value from 62 nanometer to 68 nanometer, it will cover more than 99% of the area. So typically the corners are selected to cover plus minus 3 sigma, right? Things will become more clear when we talk about duration. But now what we have done is we have plotted the channel length and the threshold voltage of devices on the two axes. Channel length being on x-axis, threshold voltage being on y-axis. Now note that a greater channel length and a greater threshold voltage means a slower device. So somewhere around here at this point the devices are slow, and somewhere around this point the devices are fast. In the middle the devices are typical. That means the devices at the slow corners are slower, will have more delay. Devices at faster corners will have faster delay, less delay. So we have chosen two corners at the two different extremes, and we hope that, or let's say we know that in older technologies, that these cover the two extremes of the process variation. Right? We are planning to make sure that complete area, this complete area in the middle is covered. Right? Obviously, the actual distribution of the devices will be clustered around the middle. Most of the devices will be closer to typical. There will be some devices which will be towards the slower side. There will be some devices which are towards the faster side. But we have to do STA at fast corner and slow corner. What it means? First important thing, it means that we are trying to make sure that only very few of the devices fail. There will be few devices which are even beyond the slow corner and the fast corner. There might be because of the manufacturing process variation. So we are trying to make sure here that most of the devices, or more than 99% of the devices, work. But again, majority of the devices, since they are lying in somewhere in the middle, this analysis will be pessimistic for them. That means we are assuming some, let's say for slow corner, we are assuming a worst case delay for some gate. But most of the gates will be around the corner, right? So they will not have that high a delay. So this analysis, STA is corner based STA is also in most of the cases pessimistic analysis. That means you are taking margins beyond the typical. But the idea is here is to make sure that almost all the devices work, or sorry, almost all the chips work, and they meet the required constraints. So by doing corner based STA, although we are pessimistic, but we are at least ensured that the idea is to make sure that the customer does not send back our defective chips. Right? That's the idea. So if we want to manufacture a processor which meets 1 gigahertz, we have to make sure that it meets 1 gigahertz at the slow corner. Right? So if we meet that and we make sure that all the timing constraints are met in the fast corner and slow corner both, most of the chips manufactured under such conditions will probably meet frequencies which are greater than, at least maybe 10 to 20% greater than 1 gigahertz. It might also happen because STA is pessimistic, right? Probably you will appreciate the pessimism or the corner based STA when we discuss about variation, right? Now, what operating conditions we might choose, right? So in all the all the technology nodes like 55 nanometer, 90 nanometer, at least we should have two corners. One is the worst case corner as depicted by this graph. At least we should have at least two corners, worst case and best case. Worst case corner process type is worst. That means NMOS and PMOS both have slow. Voltage is low, temperature is high, the cell delay is high, which is setup critical. Best case process type is best, voltage is high, temperature is low, which means that all the devices are on the faster side. It is critical for hold. We'll see why I say this. We'll see why the worst case corner is critical for setup, and we'll see why a best case corner is critical for hold. For 65 nanometer, typical operating condition can be 1.0 volt, 85 degrees C. Worst case corner in this case would be 0.9 volt, which is 10% below the VDD, temperature of 125. Best case corner could be 1.1 volt, which is 10% more than the VDD, and 0 degrees C. Temperature depends on the type of environment conditions under which chips will be used. If chips are used for space applications, this temperature would be in negative. If chips are used for household applications like televisions, mobile phones, and so on, this could be 0. So depends on the type of the type of environment condition we are targeting for that chip. So this temperature will change based on that. I already discussed pre and post layout SPA. Let's just summarize this pre layout SPA. No information about the nets. It is all estimated. It is all via load model. Most important thing, estimated net delay used for resolving bottlenecks and finalizing your SPA strategy. This is very important. So you don't wait till the post layout data comes in and then iron out the problems in your constraint. You start working from pre layout level. Post layout will take some time, and meanwhile you can finalize your SPA strategy. This is very important. Choose the worst corner, same as synthesis. Ideal clocks. What it means is that there is no clock free in place. We'll see what ideal. Ideal means that the clock reaches all the clocks at the same time. Let's say you have a single clock in your design, it drives 1000 registers. The clock will reach all the 1000 registers at the same time. In most of the case, the delay would be 0. Why? Because you don't have any information about the delay. Post layout STA uses back annotated net information, which is contained in one of these files formats, either SPEF or DSPF, done at various corners. We saw minimum you need to, best case, worst case, clock network fully implemented. The clock tree is done, and you have all the clock network in. So based on whether we are doing pre layout or the post layout SPA, a lot of things change about the clock. The clock constraints would change. We'll see them later. Other constraints would mostly remain same, but something about the clocks will change. We'll see what. Now, what are the steps of doing SPA? I mean, what the tool actually does. So what tool will do once you feed in the design and the parasitic information based on whether it's pre layout or post layout, if it's pre layout in the variable model. The tool will do 3 steps. It will first break down the circuit into a set of timing paths. We have seen a bit of we saw what timing paths are in synthesis. We'll review them in STA. For each path, delay is calculated, and these path delays are checked to make sure the timing constraints have been met. Now let's see. So a couple of important things for combinational cells. The only thing important is propagation delay. It is a function of output load and input slope. Sequential cell, apart from the propagation delay from clock to 2, you also have timing checks like setup and hold, recovery and removal. Timing checks are function of constraint pin transition and related pin transition. We have seen this in the library. If you don't remember this, please go back, look at the standard cell library and see that setup is dependent on what indexes, right? What are the indices of setup? The setup lookup table. Delay calculation. The gate delays are calculated, are taken from library. So cell delay This is the cell delay. Gate delay is nothing but the cell delay. It comes from the library, from the standard cell library. Net delays from post layout data. Delay calculation. Gate delay is interpolated from the non-linear delay model lookup table. We saw that in unit 3. Net delays are either they are bi-node models, in that case they are estimated. When we feed in the actual net delays by SPEF and DSPF, by putting in SPEF and DSPF, they are calculated. So SPEF and DSPF, they do not contain delays. They contain the R and C information, the resistance and capacitance information of each and every net. Using this R and C value, the STA tool has to calculate the delay, right? So they are calculated using algorithms, and these algorithms, let's say prime time, what prime time will try to do, it will try and match the spice. So spice is the reference. It will try and match the delay calculation to the algorithm will try and, so spice is very time consuming. It will try to do spice on the complete, so the most accurate way, the most accurate static timing analysis should be done using spice. But if you do that for a full chip, it will take days and days. What STA tries to do, it tries to make the process much more faster. Obviously, in the process of making things faster, so one thing, it doesn't work at the NMOS level, NMOS, PMOS level, transistor level, it works at the gate level. That helps a lot in terms of abstraction. Second thing, it will use some fast algorithms to calculate the net delay. But also it will try and make sure that these delays are within, let's say, 1 or 2% of the spice data, and they do not deviate much. So here the reference point is spice. But you don't have to worry about spice when you're doing STA. This is the job of the tool, right? Not the job of the user. So the tool, for example, prime time claims that the delay calculation is within some percentage of the spice. So we'll just take their word for it and do our best, right? Let's take a look at the timing parts. So the tool will start at the input. It will stop at the first sequential element it encounters. Input to register path. Again, it will start at the clock input. Add the register. It will again stop at the data input of the any flop it founds. This is called register to register path. Again, it will start at the clock input until unless it finds the output port. Obviously, there should not be any sequential logic in between. So the last with this kind of path is called register to output path. If it does not find any sequential element and directly encounters output path, it is called a combinational path or a feed through path. There are 4 basic kind of paths. There are more than that. Path start point is the launch part. We have seen that the timing report will show this as a launch part. It starts with either input pin, input port, or the clock pin of a sequential element. So in this case, it's either a port, this part, or the clock pin of the sequential element. Endpoint, the capture part, can be either output port, it should be port here, output port, or the data pin of a sequential element. So path is captured here, here, and here. Checking is always the capture part, launch part forms the data part, right? So we have seen timing reports. We will see a lot more in this unit. Timing paths are always grouped according to some principle. The principle is that the capture, they are grouped into path groups by the clocks which are controlling the endpoint. So for example, path from A to D here, path starting at A, being captured at D, the path group is clock 1. So path 1 is from A to D of this FF2, and path 1 comes under the group clock 1 because the capture clock here is clock 1. Path 2 is from FF2 to FF3. It comes under the group clock 2 because the capture clock is clock 2. Path 3 is from Q of this, from clock of this clock 2 to Z. Now path 3, if you do not give any output delay on Z, it will come under the default group. Similarly, path 4 starts from A, ends at Z, and assuming we haven't specified any output delay on Z, it will come under default. However, if you specify output delay on Z using, let's say, clock 2, it will come under the path group clock 2. So STA tools like prime time, they will generate timing reports and sort them by the path groups, right? So it will show the timing report within each path group. The complete list, we have seen register to register path. How are they constrained? By just defining the clock. We have seen this in Unit 3. Please review that. We will also see some equations in the following slides. Input to register path can be constrained by defining the clock and the input delay. Register to output paths are constrained by defining the clock and the output delay. So what do you do? First, you define clock, you define proper input delays, you define proper output delays. This will constrain most of your paths. Input to output paths, fully combinational paths can be constrained using virtual clocks. We have seen an example, or using max delay maintenance. Then there are separate path groups for clock gating. Clock gating paths are special because the clock gating element itself is special. Then async default, recovery and removal. So these are again separate path groups. So 4, register to register, input to register, register to output, input to output. Apart from these basic 4, you have clock gating, async default, and a default path group. Right? So in all there are 7. Again we have seen this. Net delay is a total time which needs to charge or discharge all the parasitic capacitances. Cell delay is nothing but the delay it takes the signal to traverse from input to output. So the path delay is the sum of net delay and cell delay. Now there are various terminologies. Most of them you are already familiar with, but I'll expand each of this. Setup and hold times, recovery removal, pulse width, signal skew, clock latency, clock skew, stack and critical path, and these are timing exceptions, false path and multi-critical path. Let's look at them. So I'll define this again. Setup and hold times for an edge triggered element like a flip flop. The time interval before the active clock edge during which the data should be unchanged is called a setup time. So in this diagram, in should be stable at least setup time before the clock edge. This is a constraint. This is a property of the sequential element. Similarly, hold is the time interval after the active clock edge during which data should be unchanged. This is called hold time. Setup and hold are the properties of the sequential element. They are calculated from the lookup tables given in the lab. Right? You've seen that. I call this a classic timing problem between a register FF1 and a register FF2. The delay of the combination logic is TCOM here. TPD is the propagation delay of flip flop 1. TS and TSH are setup and hold times for flip flop 2. So now let's see the timing equations. We'll review the timing equations. We'll see how the setup and hold time actually affect the checking and what happens if they vary. Now setup check. TPD plus TCOM, we'll go back and forth. So the data will be launched by the flip flop 1 at the active edge of clock. It will take TPD delay to go to traverse the flip flop, plus it will take TCOM delay to reach the D. So TPD plus TCOM, D0 is the old data, D1 is the new data. Flip flop 1 is launching D0. So flip flop 2 gets D0 after TPD plus TCOM. Okay, let's review the setup and hold timing constraints for the sequential element like a flip flop. So for such an element, the time interval before the active clock edge during which data should not be changed is called a setup time. Let's look at the figure. So this is the active clock edge. Setup, at least the setup time before this active clock edge, data should remain stable. The hold time is a timing constraint, represents the timing constraint after the active clock edge during which the data should not change. So data should remain stable at least setup time before the active edge and hold time after the clock active edge. During this window, data should not change, or to make sure that the sequential element captures the data properly. Now let's look at the classic timing problem. That means data is being launched by a flip flop FF1 is being captured by the flip flop FF2. TPD is the propagation delay for FF1. TS and TH are the setup and hold time constraints for FF2. TCOM is the delay for the combination element in between. Now FF1 will launch data at the active edge. It will launch D0 and after the delay TPD plus TCOM, sorry, it will launch D1, not D0. D0 is the old data, D1 is the new data. So flip flop 1. So let's say after TPD plus TCOM, D1 will start reflecting at D. So here at this point, at this data pin of FF2, flip flop 1 will launch new data D1. After TPD and TCOM, data will appear at D of FF2. Here, the data will start changing here. Since data changes here, it should, and to meet the constraint, the setup constraint of FF2, data should not change in this TS window, right? So, if we represent this using the timing equation, it is something like this: TPD plus TCOM, that is the combinational delay, plus the delay of the launching clock, should be less than TCK minus TS. That means this is TCK, this complete the delay between this active edge and this active edge. We subtract the setup time because the data should not change TS before this, so TCK minus TS, and TPD plus TCOM should be less than this, right? Now we will, so total path delay is TPD plus TCOM. It is called the path delay, combination delay plus the launch, the sequential elements launch delay. Now, see, look at this equation. I'll underline this equation. The left hand side, that is this side, is the path delay, and this side is the constraint. The equation is of the form path delay less than constraint. Since it is less than constraint, so that means TCK minus TS is nothing but a maximum value that the path delay can have. TCK is in most of the cases it is fixed. I am designing a CPU for 1 GHz. TCK will be the time period of the clock, which is a 1 GHz clock, right? TS in most of the cases it is a value, it is a very tight range. TS is nothing but the setup time of the clock, and setup time of the clock depends on the transmission value of the data pin and the clock pin. So it is constrained within a very tight value. It is not in user control. It is not design dependent, right? So this TCK minus TS gives us the maximum time this combination logic can have. In fact, TPD also is not under user control to a great extent, right? Because it's just the delay of the single clock, right? What is design? What design comes in while designing the combination clock? So TCOM is actually under user control. So your propagation delay, your path delay should be less than some maximum value. That is why setup check is also called max delay check. What is slack? Slack is constraint. What is constraint? TCK minus TS. What is delay? TPD plus TCOM. If the slack is positive, timing is met. If the slack is negative, timing is violated. Now what happens if setup violates on a chip? Let's say I designed a CPU. I had some problem in my STA. I did not know how to do it properly. The chip is fabricated and now does not work at 1 GHz. We try and make it now. Externally, we can control TCK. So there is a crystal on chip which we can program for the clock. Now what I do is I program it for 900 MHz and see if it works. And if the setup violates, so now by increasing the value of TCK, at some point it might start to meet. So even if the setup violates in STA, when the chip is fabricated, the chip might work at a lower frequency because setup is clock frequency dependent, right? That is why when you go into market and try to purchase processors, the processors come under various frequency grades. Right? So you might get a core 2 duo for 3.2 GHz, again for 3 GHz, 2.8 GHz, and 2.8 will be cheaper than 3.2, right? So you all know that mostly. So are they different chips? No, they are same chips, but and STA was done properly. It does not mean that STA is not done properly, but what may happen due to process variation? Some of the slower chips, they don't meet the 3.2 GHz. So, but they meet 2.8 GHz. Good, we can sell it for less, right? So the chip still works in case of setup violation, but at a lower frequency, right? Again, now let's look at this equation from the corner STA point of view. Now what happens at the burst corner? At worst corner, TPD is more, TCOM is more, TCK is fixed. It's the performance thing. It's the clock frequency that we specify. TCK is fixed, but TPD and TCOM increase, right? TS might also increase a bit because the temperature is increasing. So, if we make sure that all our setup constraints are met at the worst corner, then we have made sure that they also work at the minimum, because TPD plus TCOM attains a maximum value at the worst corner. This is why setup is called a max delay check. This is why the corner based STA mentions that. Let's go back to the corner based STA. Worst case corner is setup critical. That means this is the corner which would be bad for setup. You have to make sure that setup works in this corner. So just by looking at this equation, we are able to deduce that setup check is a maximum value check, and it is most critical at the worst case. Okay. Let's go to hold check. Now what hold? So just look at this figure carefully. Now see that what setup check is trying to do. It is trying to make sure that FF2 captures D1 properly. That means D1 should be set up properly before FF2 can capture it. Before okay, in this case the diagram is not too good. The negative edge is shown as the capture edge. This edge is shown as the capture edge, but it doesn't matter. This could we could shift the pauses to here if you want that. So it is making sure that this setup check that FF2 captures data properly. What data? The data D1, the new data, what FF1 launches. Now let's look at the hold slide. Now in hold, what is the check? The check is that D0, FF1 will launch new data D1. So D0 will transition into D1 at some point of time. What is that time? It is nothing but TPD plus TCOM. So same as the setup like thing, D0 transitions into D1 after TPD plus TCOM. Same thing goes for hold. But now we have to make sure that during this transition D0 to D1, this transition should only happen after the TS time, after the hold time. Right? I'll repeat. It's very important to understand that FF1 launches data D1, old data was D0, D0 transitions into D1, but the constraint here is that data for FF2 should not change within this window, within the TH window. So TPD plus TCOM should be greater than TH. What this check is telling us that this is making sure that old data D0 is captured properly by FF2. Right? So the setup check will make sure that the data is set up before the clock is properly. The hold check will make sure that data is held for some time. Data is held for some time. D0 is held for at least TH time before it could transition into D1. In terms of equation, TPD plus TCOM should be greater than TH. Again, let's analyze this. Part delay TPD plus TCOM, same as before. TH comes from the library, hold time constraint. What is the equation type? Equation is this type. Part delay is greater than a minimum value. So hold check will constrain the part delay for a minimum value. That is why this check is also called min delay check. Now if we combine both setup and hold equations, we see that part delay TPD plus TCOM remains same. The maximum value is TCK minus TS, the minimum value is TS. Right? So for every path, for every timing path, the part delay should be, every time you will see that in the timing reports. For every timing path, there is a maximum value and a minimum value. Max check or max check is also, setup check is also called a max delay check. Hold check is also called a min delay check. Right? What happens if hold violates on a chip? Nothing. You can throw the chip. You can do nothing. Why? Because there is nothing you can play with when the chip gets manufactured. Everything is fixed. There is no clock frequency here to work with. This is why when you go into the industry, when you start working on real chips, you will see that the setup is checked at probably 1 corner or 2 corners. Hold is checked at 6 corners, 8 corners. Why? Because we are very sensitive about hold. There can be a setup violation. You can manufacture a chip with a small setup violation, but not with a hold. You have to make sure that all the hold timing constraints are met. Again, we will try to map this equation to the corner based SPA. Now, what happens for a burst corner? For a burst corner, TPD is more, TCOM is more. It is good for hold, right? There is more delay, so it will meet the minimum values, minimum timing constraint. So no problem. When you go to best case corner, TPD starts decreasing, TCOM starts decreasing. So the best case corner is bad for hold. That's why we say that it is hold critical. The best case corner is hold critical. So you should be very clear that setup check is the max delay check, hold check is the min delay check. What is STA? Hold should be met in best case corner, setup should be met in worst case corner. In fact, let's say you choose n number of corners. Bottom line is all the setup and hold constraints should be met in all the corners. That is the idea. But we know that worst case corners, the corners that have more delay on cells will be more critical for setup. The corners that have less delay on cells will be more critical for hold. Right. So again, the bottom line, max delay and min delay. These are the two things you have to remember. Max delay is setup, min delay is hold. All formulae, all timing paths you can understand if you understand how the equation is represented. I'll repeat. Path delay less than maximum constraint is the max delay check, which is this TPD plus TCOM less than TCK minus PS. For hold, path delay is greater than the constraint is the min delay check. That's it. That's the whole summary of STA. Now what we will do, we'll apply this principle of max delay check and min delay check to all other timing paths that we'll see, and we'll see how this matches up. Right. Now let's talk about input to register path. So input to register path, the input comes from external world, external to our design or external to our chip. So there's something called input arrival time, which defines the time interval during which data signal can arrive at a pin in relation to the active clock edge that triggers the data transfer. Now let's say this is the clock on which the external device operates. External device will launch the data, and this data is captured inside a chip. For both rise and fall, there will be a timing window during which the data can transition. This is the timing window. So the data can come. Let's say we are talking about let's say some interface, let's say IIT or something like that. Let's say the data can come 2ns after this clock edge, and 2ns can be minimum value, and for maximum it could be 5ns. So what we are saying is that the interface is such that so the external device is also again a chip. It will have process variations. There will be wires on the circuit board that will connect the two chips together. It will have some variation. So we are saying that the data can arrive at your boundary between 2 and 5 nanoseconds of the trigger edge, right? So the min value is 2, the max value is 5. So this is the way the input arrival time is characterized. Now what is input delay? Let's look at the equations now. So now we know that okay, there is something called input arrival time, and in most of the famous interfaces, this input arrival time or input delay is already given. It's already published, right? So you can use the same value directly. You just have to make sure that you use the proper max value for the max delay, proper min value for the min part of the delay. In some cases, you have to estimate this input delay. Now this slide will tell you how to estimate the input delay. Now external world, let's say the delay is T in, the input arrival time is T in. After T in, the data arrives at input. T combination, this is internal to your chip, and FF1, since it's captured, we are worried about the setup time here. It will have PS and TH. PS and TH are the setup and hold time. Now for setup, again the equation is the same type. Tn plus Tcom should be less than Tck minus Ts, right? So Ts is the setup time constraint. This is the max delay equation again. Now what I am doing here is I am rearranging the equation in such a manner that on left hand side I'll keep what I need to evaluate, what I need to estimate. I need to estimate the input delay part. So I'll keep the T in something which is exponent to our world. So I'll keep T in on the left side. On the right side, I'll keep all that which is internal to our chip and known. So Tcom, Tck and Ts are all internal to my design and are known to me. So Tn is less than Tck minus Ts minus Tcom. Please note again, it is a setup timing constraint. You need to represent this equation in the form of estimate less than constraint, less than sign, estimate less than constraint. Again, this is the estimate part, this is the maximum that it could have. So estimate less than the max delay constraint is the max delay equation or the setup equation. So how do I estimate an input delay? Now let's say the clock frequency is 10 nanoseconds, and let's say setup time of this clock is 1 nanosecond, and let's say I have some combination element which takes, let's say, 3 nanoseconds. So frequency of 10, setup timing constraint of 1, combination delay of 3. I know how much. So by using this, I say 10 minus 1 minus 3. That means I have 6 nanoseconds that I can give to the experiment. This is the way you can estimate input delay if the input delay is not already known for famous interfaces, right? Now we'll do it for hold, right? For hold, again, we'll represent the equation in terms of estimate greater than a minimum value, right? For hold, Tin plus Tcom should be greater than Ts for this clock. No clock frequency comes into play here. Again, I'll rearrange. What I know, I'll keep on the right hand side, which will form the constraint part. What I'm trying to estimate will come on the left hand side. Again, estimate is greater than some value. What is the value here? Ts minus Tcom. Now let's look at it in the practical sense. Now Tcom here, if you have some combination delay here, hold time of clocks are not big values. They are for, let's say, for 45 nanometer, they will be in the range of, let's say, 0.1 nanosecond, 0.2 nanosecond maximum, right? So if you have a significant combination delay, you don't need to worry about hold. Why? Because this is already met. Tin would be greater than Th. So even if you have an input delay of 0 for the hold case, this value here would be negative because T combination, let's say, is 1 nanosecond. Hold is, let's say, 0.1 nano. So this will be negative, and the value of 0 will, this condition would be met. So if you have combination delay from input to the first clock that captures it, it helps for hold, does not help for setup, right? So for setup, since the constraint is maximum, we want the delay to be less. For hold, we want the delay to be more, and that is the ST problem. We need to make sure that all part delays meet on both sides, on the min side as well as on the max side, right? Let's look at output register to output path. So something called output required time. On the input is what? Input arrival time, right? On the output side it is output required time. Output required time specifies the data required time on output ports. We will launch the data from the clock, and required time directly specifies the timing through logic zero. Let's see it in terms of equations. Again, now on the output side, since we are talking about the output side, we have a clock that is launching data after TPD. We have a combination delay, and let's assume on the external world there is a clock that has timing constraints of TS and TH. Now let's look at the equation. T out is, let's say there is some combinational cloud here on the output side with T out. Now I'll arrange. What is the part delay? TTD plus Tcom plus T out plus TS is less than TCK. You could also have TCK minus TS at the same thing. Again, I'll rearrange. On the left hand side, I'll keep what is the estimate part. What is the external world? What is the external world? T out and TS. And I'll rearrange. So T out plus TS should be less than TCK minus TTD plus Tcom. What this tells me is that let's say there's a clock frequency again 10 ns. I'll choose this 10 nanoseconds. Let's say the propagation delay is 2 nanoseconds, combination delay is 2 nanoseconds. So 2 plus 2 4, 10 minus 4 is 6. It tells me that I can give 6 nanoseconds to the output side, because I am consuming 4 nanoseconds inside, right? So this will help us in giving and estimating the output delay for the external world. Hold is much more interesting and slightly complex. Now for hold, what is the part delay? TPD plus TCOM plus Tout, same thing, part delay is same. It should be greater than TH. This is the equation, right? I will rearrange. Left hand side is the estimate part, TH is estimate, TH I don't know, so I'll take TH on the left hand side, so Tout minus TH. On the right hand side, I'll have minus TPD plus TCOM, right? The set output delay. So how do you define output delay? We say set output delay. How do you separate between setup and hold? We say minus max for setup, minus min for hold. Please remember, if you have a constraint like set output delay minus min, that is for hold, and the value there is positive, you need to take a relook. You need to check again, because this equation tells me that you have to give a negative value. Negative value does not mean, it only means that this is the way STA tools understand data. How do we arrive on this? We have written the equation like this. We have rearranged the equation to conform to some standard. What is that standard? The standard says that your estimate should be greater than something for hold. How do we arrive? So we rearrange, and the right hand side value is negative. Set output delay minus min should almost always be negative. If it is positive, if you are giving a positive value, you should rethink. Giving a positive value most of the time is a problem, is an error, and it will result into optimistic analysis. Please be very careful. Go through these equations. You have to just remember two things: how to write equation for a max delay, how to write equation for a min delay. These equations are almost of the same format as the register to register equation. Right? Other things, important things that STA checks are pulse width and signal slew. Pulse width is the time between active and inactive states of the same signal. When are pulse width important? Pulse width is very important for memory. So memories, the hard memories, that is the full custom memories, like single port or register files, have a min pulse width check on the clock. That means, what it means is that if you give a clock which has a pulse width which is smaller than something, either for the high edge or the low edge, the local for the high pulse, the memory will not work. So memory needs a minimum pulse width on the both high pulse and both the max pulse and the min pulse. So both on the, it needs a min pulse value or both the high and the low pulse, right? So for example, a memory might have, and this check is independent of the setup and hold, right? So you need to make sure that so if you do report constraints on a solve volatil, this report will tell you all the setup violations, all the hold violations. It will also tell you all the min pulses. Right? Again, there is a signal slew. Amount of time it takes a signal to transition from 0 to 1 or 1 to 0. It takes into account the uncertainty in transition. So this can be from either 10% of EDD to 90% of EDD or 20% of EDD, 80% of EDD. This is defined by a technology library. We have seen that in Unit 3, right? So these are the two things apart from the setup and hold constraints that STA tool checks, right? Signal slew, there is a max transition check that checks the signal slew. And also please note that slower transitions we saw result into more short circuit power, so they are not recommended. So it's good to have faster transition times. There's something called clock latency. So clock latency is the difference between, so this is the port of the design where we create the clock. Now let's say you have a flop. Clock A just tells me that this is one flop, this is another flop, this is third flop. The clock to the flop A, flop B, and flop C reach through 3 different networks. Now let's say there's a path from clock A to clock B, right? Now the latency, what is latency? Let's consider clock A in isolation. Forget about clock B and clock C for now. So the latency at clock A, it will have two values, a rise and a fall. Now let's say clock rises here, so it will rise here, rise, fall, rise, fall, rise. There are 4 inverters in place, right? Rise delay here is 7, fall delay is 4. So what is the total amount of delay the clock takes from CLK to CLKA? It has 2 rise transitions and 2 fall transitions, right? So 2 rise transitions between 7 plus 7 14. 2 rise transitions means 14 4 plus 4 8. So 14 plus 8 is 22. So the clock latency at CLKA point is 22. Similarly for CLKB, clock rises here, clock falls here, clock there is a buffer here, clock falls here, right? So the fall latency at CLKB is 4, it is fall, plus fall again 8, because clock rise means fall here, and this rise and fall means regarding the output, relation to the output. So rise latency at CLKB, how do we calculate rise latency? Let me clear the data first. So how do we calculate rise latency? Rise at CLKB, we need to calculate rise latency. Rise at CLKB means rise at this point, rise delay is 7, rise at this point means fall at this point, fall is 4, 4 plus 7 is 11, right? So this way you can calculate latency. Latency is just the time it takes from the clock creation point to the point we are interested in. Clock A is mostly the capture at a particular clock. The second thing which is called clock skew. Now clock skew is in relation to 2 points. The difference in delay between 2 points. These two points being the clock pin of the 2 registers. So when we talk about skew, there is a skew between clock A and clock B, clock B and clock C, clock A and clock C, clock B and clock C. So any 2 pins you pick up, any 2 clock pins, the difference in arrival times is the clock skew. So how do I calculate clock skew? I calculate like this. I calculate, for example, for clock A and clock B, you calculate the rise latency at clock A, rise latency at clock B. So the clock rise skew would be rise at clock B minus rise at clock A, the absolute value. Similarly, you can calculate fall. So you know the clock latency at clock A, clock B and clock C. That means rise and fall latency separately. And clock skew between any two points would be simply the difference of the clock latency value. We will see how clock skew is very important. We will see why, right? When we look at the post layout data, we will see how clock skew is important. Clock skew changes the way. So now let's go back to the setup and hold timing. Now let's say setup. Go to this window. Now here we are assuming that clock is arriving at the same time at the 2 clocks, FF1 and FF2. At FF1 and FF2, we are assuming that the clock arrives at the same point. This is called ideal clock. This is the pre-layout point, right? And what about the post layout? The post layout, the clock edge, the active clock edge will be either coming late or coming earlier. What if it comes earlier? If it comes earlier, your window is shortened. Your setup timing is more constrained, right? Let's talk about hold. What happens if the capture clock comes later? You are more constrained for hold. It's a problem for hold if the capture clock comes later. So this is where the clock skew is very important. In post layout data, prime time calculates the clock latency for every clock and it knows the clock skew between every pair. It doesn't calculate clock skew separately, but since it knows latency at every point, in the timing report you can see the clock skew, right? So this is why clock skew is very important. We will see in how do we in pre layout how do we estimate clock skew, and in post layout how do we handle clock skew, right? So we saw about clock latency, clock skew. We have discussed slack and critical. We have discussed what is slack. Slack is the difference between the path delay and the constraint. Negative slack means that constraint have not been satisfied. Positive slack indicates that the constraint is met. SK tool calculates the slack of each timing path in order to find the critical path. Critical path is any logic path that violates timing constraints. Any path, that means any path with negative slack is called a critical path, right? There can be multiple critical paths. We saw that how DC handles critical paths. If we try to reduce the worst negative slack and the total negative slack on the critical paths. That is the idea of optimization. We have seen this. This slide just gives a summary of how do we calculate slack. We have seen that in setup and hold timing equations how the slack is calculated. Slack is nothing but you can review the slide at later. It tells that how the slack is calculated for input register, register to output, register to register, and input to output blocks, right? So you can the first thing, the most important thing for you is to understand the equations I have discussed before. If you understand the equations, you can actually write equations for any kind of timing path, and you can understand how setup and hold timings are checked, right? Even on complex paths, there are some paths which can get complex. There are certain timing, certain interfaces that have some complex timing steps. But if you know how to write the equations for setup and for hold, you can understand any path. You can understand any timing report. What are recovery and removal times? Recovery time is the time available between the asynchronous. It is a specific to asynchronous signals. Setup and hold timing is characteristic of synchronous signals. Recovery and removal is characteristic of asynchronous signals. It is a time available between asynchronous signal going inactive to the active blockage. For example, reset n going inactive. It should go inactive at least some time before the active blockage. This constraint is called the recovery time. It is very similar to setup. Removal time is similar to hold. That means it is the timing between active blockage and the asynchronous signal going inactive. The difference between recovery, removal, and setup hold is this: setup and hold is for both the edges. Active, I mean, there's nothing called active and inactive in case of synchronous signals and data signals. Both data going from 0 to 1 or from 1 to 0, for both there will be setup and hold time. But for asynchronous signals like reset, only the inactive, the transition going from active to inactive is important. Why? Because when it goes to active, the functionality is very clear. Whenever reset goes into active, data goes to 0. That's it. No timing constraint. But when the signal goes inactive, now let's say the signal is going inactive here, the reset end. This clock edge is the active clock edge, and we have to make sure that whatever data transition happens here is reflected on the clock. But if the reset violates here, if it changes somewhere, let's say here, and it violates the recovery, the Q of this clock will remain 0 because it still considers reset to be active because the recovery condition is not met. Similarly for removal also, this is the active edge, but this edge should not have any effect. Why? Because reset is still active here. But let's say it is removed earlier, the reset is removed earlier, then this clock edge might affect the data. But since the reset is 0 here, data should be 0. But since you have removed it earlier, it might be a problem. So that is why the edges, the reset edges going to inactive are important, not the active going edges. This is why you will see that recovery and removal are only in one direction. Let's say you are active low reset, recovery is only characterized for reset going to home, going inactive, and not the other way. You can open up the standard cell library, you can go to a flop and you can see how reset and how recovery and removal time are represented. Let's talk about timing exceptions. I will briefly introduce false path and multi-cycle path. These three I will talk about later. So what are false paths? False paths are paths in the design that exist. According to STA tool, they exist, but they are not possible. They are not sensitized in any input conditions. Let's see one example. Let's say you have two muxes here. Both are controlled by the same select pin. Right? Both are controlled by the same select pin. So if select is 0, A will be passed on, and here C will be passed on to output. Right? If select is 1, B will be passed on to C, and again C will be C. There is some branch, so there are two branches of C. One is going through buffer, the other is going directly. It will be passed on to output. Now see this path. Path starting from A and path starting from A and going to this branch. So this path, consider this path, starting at A and going to this branch. Is this path possible? No. Why? Because the selection is same. So if select is 0, this will go through, but this will be blocked. On select, when select is 0, let's consider two cases. Select 0. This path is blocked because this is a one path. This path is enabled. So this path is not activated. Now let's consider the case when select is 1. This path is activated, but this path is not. So this path is not possible. But why then this path is even showed? So if you don't do anything, prime time will show a path which are not possible design wise logically. So prime time will show this path, this path, this path, and this path. It will show all possible paths. Why? Because it is static in nature. It does not consider logic values. It considers all possibilities. It does not consider any logic value on S. Right? It will assume S is not. There is no value on S. S can be anything. Therefore, all paths are possible. It does not consider the case where S is controlling both the muxes. So, as a user, it becomes our job to tell the tool that what to do. So, what we could do, we can tell the tool that hello, from this path is not true. This path is not true. You can do this in multiple ways. There are multiple ways of doing things. One of the very famous ways called false path. You could say that false path, and you can say from and to. There's one more way, we will talk about it later, but this is meant by false path. False paths are paths in design that are not logically possible but still showed by the static timing analysis tool. Okay. One more example. Let's say you know that there's some prop in your design which never changes its value, which is always static. There can be multiple reasons. This can be software programmable, and software programmable registers are mostly one time. They change only one time, or they don't change at all. They have this fixed value. Any path, any setup check starting from this block, or any hold check starting from this block is false. Why? Because the value never changes. So no change in value means that it is not going to trigger any setup or hold check. So but prime time does not know that. STA tool does not know that. You have to tell the STA tool that that's false path from this register. This is one example. We'll see a lot more this in lab sessions. Other type of exception is the multi-cycle path. Multi-cycle paths are data paths that require more than one clock period for execution. Now let's say you have a big combination logic, and you know that this is going to take more than one clock cycle, and you don't want to add pipeline here. You don't want to add any pipeline. So you can tell, and it will violate, right? It will violate. So this constraint is both false paths and multi-cycle paths are also important for synthesis. You don't want synthesis tool to optimize false paths. You don't want synthesis to unnecessarily work on a combination cloud logic which you know it is going to violate. So you have to tell the tool that set multi-cycle path minus from this minus to this will take more than one cycle. We will see commands later. Don't worry about the commands. But this is a way you can tell the tool that my logic will take more than one copy. So we'll see. This is very interesting. We'll see how STA tool handle this. Right? How does the report timing looks like? The idea of this session is just to introduce you to the concept of multi-cycle path and false path. Again, what STA tool checks are boundary conditions. They are same as what design compiler does, but please note STA post layout STA has actual net parasitic. So also you could specify, so the boundary conditions are something which you could specify proper STA. Again, they are same commands: set load, set driving cell, set input point, same as what we discussed in unit 2. So let's summarize STA flow. Very similar to synthesis, nothing different. Read design data, library design parasitics. This is important here. This is new here. Apart from synthesis, post layout STA. Apply constraints. Now these constraints here will be slightly more than what we did in synthesis. We'll see why. Because we are talking about post layout. Some things will change. The nature of clocks will change. So we will see how do we modify or add to these constraints, what important things we need to focus on, but know for sure that the constraints here will be slightly more than what we applied in P, right. Third thing, we have to check that design is properly and fully constrained and there are no DRC violations. What happens when there are DRC violations? You cannot rely on timing data. I've talked a lot about this previously. Please go back if you are confused about how DRC violations cause unreliable timing results. You can go to UNIP and go through the sessions again. Last part is that we report all the timing violations. We report what is the setup, the report timing setup, or if we do a report timing for hold, we do report constraints on a solve violator. We make sure that move on. Right. There is an exercise. I will not solve it here, but the clock is a very simple thing. You can apply your equations here. This figure will help. It will tell that this is a setup launch edge, this is a setup capture edge, this is a hold check, this is a hold check. These two edges will be hold check, or these two edges doesn't matter. So what you could do, you could take one of the labs and you can do a report timing and understand that what this figure tells is actually matches with the report timing. Plus you can use the equations I have talked about before in the previous slides and calculate what you should calculate. You should calculate setup slack, hold slack. You can estimate input delay and estimate output delay. Please note now what is special here is that I have included the max and min values for both. So the combination logic here will not have the same value for the best case and the worst case, right? The combination logic will have a greater value in max case, which is 5ns here, and a lesser value in the for the best case scenario, which is 3 nanoseconds. Clock period does not change. I am assuming that setup and hold constraints don't change, right? Clock to Q delay, again the clock delay is going to be more for worst case corner and less for the min case corner. Calculate setup slack, calculate hold slack. Please make sure to use the correct values. Estimate input delay. So there is no combination logic here. Assume that there is zero combination logic here and zero combination logic here. Assume this goes to an output port directly and assume this comes from input port directly. You should be able to estimate input delay and estimate output delay. Please do this for all both the max corner and the min corner. Okay. So I hope you will be able to solve this very easily. You just have to go back, understand the equations, come back here and solve it. Just a 2-minute job, right? Summary. So what we discussed in the session was about the concept of SPA, how the tool will break all the paths. It will consider all the paths. It will break each of these paths into resistor and resistor and input in the path groups. The path group is characterized by the capture clock. SCA has two parts. First is delay calculation, cell delays. Cell delays are calculated from library data. Net delays come from the parasitic file. We'll see more about that in one of the sessions. So delay is calculated and then delay is checked against the timing constraints. What are timing constraints? There are of two types: max delay constraint and min delay constraint. Max delay constraints are usually checked in the worst case corner. I mean, the worst case corner is critical for max delay constraint. Max delay constraints are of the setup constraint type. Min delay constraints are critical at the worst case corner, and min delay checks are also called the hold check. That's all for this session. In the next session, we'll discuss more about the parasitic and we'll see a lot more about the clocks. Thank you.